Assalamualaikum and hi everyone. So this is a new video for a new chapter which is chapter 3 Electrochemistry. In this video we're going to talk about subtopic 3.1 Galvanic Cell, and at the end of this lesson you should be able to first define electrode potential, draw a voltaic or galvanic cell, describe the operation of a voltaic cell, state the function of salt bridge, express half cell equations and the overall cell reaction equations, illustrate a galvanic cell using a cell notation. So let's start. We're going to start off this subtopic by talking about electrochemistry, the topic itself. So what is electrochemistry? So electrochemistry is a study of a relationship between chemical change and electrical work. Okay, so by the name itself, if you look here, it's electro from electric and chemistry. So we want to relate the chemical change from a chemical reaction with the electrical work, with electricity. Okay, and then in chemistry, how do we produce electric? So electric is basically produced when we can produce electron, when there is electron flow. When electron can move around, we can produce electric. Okay, we can produce electricity. So now let's move on to the next part. So to study on how we can get electric from a chemical reaction, we're going to look on the redox reaction. So redox reaction, we already learned this in the first chapter of semester 1. So we just take a look on what's the definition of redox reaction. So it's a combination of two half reaction of oxidation and reduction process which occur simultaneously. So we have oxidation. I hope you still remember what is your oxidation process and what is your reduction process and how to write down the oxidation and the reduction equation. So to refresh your memory, so let's take a look one by one on the reaction. The first one, we have oxidation process. So what is oxidation process? Is when the reactant release or loses electrons. So for the oxidation and the reduction process, we're going to focus on the reactant. Okay, at the same time, okay, if you look over here, if that particular reactant undergoes oxidation, at the same time, that particular reactant is called a reducing agent. Why is it reducing agent? Because it makes the other reactant reduce while itself being oxidized. Okay, and then if an oxidation process occur, the oxidation number of that particular compound will increase. Now, for reduction process. So reduction process is when the reactant accepts or gain electron. Okay, so that particular reactant, if it undergo reduction process, we call it as oxidizing agent. Okay, here we call it as oxidizing agent if it undergoes reduction. Why? Okay, this is because it becomes an oxidizing agent because it forces the other reactant over here to undergo oxidation. Same goes with this one. Why the reactant undergo oxidation? A reducing agent because it makes the other reactants over here to undergo reduction. Okay, so this is an example. So I have here zinc solid plus 2H plus aqueous to produce zinc 2 plus aqueous and H2 gas. So which one will undergo oxidation and which one will undergo reduction? So if you look over here for the zinc, so if in an exam, how are you going to determine either it is oxidation or reduction. So refresh back on what we did on the first semester. So what you can do is pair. Okay, please pair with the same element, meaning zinc with zinc, and then hydrogens with hydrogen. Okay, and then write down the half equation. So this is what we call as a half equation. So zinc, to produce zinc 2 plus 2 electrons. So this is the half equation that occur. Okay, how do we know is it oxidation or reduction? So look at the position of the electron. If the electron is on the right hand side, meaning it releases electron. So this is an oxidation process. So let me label here as oxidation. Okay. So an oxidation process where, if you look over here, zinc releases or loses 2 electrons. Okay. So zinc is the reducing agent and become oxidized. Okay, so please take note over here, the reactant. Only the reactant can be our what we call as agent. Okay, we have two types of agent, reducing or oxidizing agent. So if that particular component, for this one zinc undergo oxidation process. So we call zinc as reducing agent. Why? Because zinc will undergo oxidation. Okay. So if you look over here, the oxidation number of zinc increases from 0 to plus 2. So there is increase in oxidation number. So that's why zinc undergo oxidation. Okay. Now let's take a look for H+. So H+ over here, if zinc undergo oxidation, so automatically it will undergo reduction. Okay, so H+ will undergo reduction. So let me just label it here, even though we have our label up here. Okay, so 2H+ aqueous plus 2 electron to produce H2. So if you look over here, what happened is H+ accepts or gain electrons. Okay, so H+ accepts 2 electrons to become H2. So what happened when H+ accepts electron? So we call H+ as the oxidizing agent. Okay, here zinc is reducing agent. So over here, H+ is the oxidizing agent. Why it is an oxidizing agent? Because H+ itself will reduce, will become reduced, will undergo reduction. Okay, so like I mentioned just now, why is it an oxidizing agent? Because H+ over here makes zinc undergo oxidation. And why is zinc a reducing agent? Because zinc makes hydrogen, H+ over here, to undergo reduction. Okay, agent makes something do something. Okay, so next, the oxidation number of H+ decreases from +1 to 0. So this is just to show that it is a reduction process where you can see the oxidation number decreases. To study electrochemistry, to look on the changes between the electrical power and also the chemical reaction, we're going to observe by using an electrochemical cell. So what is electrochemical cell? It's a system that incorporates a redox reaction to produce or use electrical energy. So meaning here, what does it mean when it says a redox reaction to produce or use electrical energy? So we will have two types of reaction. So it's either from a chemical reaction, okay, we will get electrical energy, or from electrical energy we can get a chemical reaction. Okay, So this is what we will get from our electrochemical cell. So different electrochemical cell will give us different types of reaction. So how many types of electrochemical cell do we have? So recall back, this is something that you have learned back in your secondary school during your SPM. So the first type we have over here is galvanic cell, or we also call it as the voltaic cell. So throughout this video, you will heard from me using galvanic cell or voltaic cell. So if I mention either one, it's the same thing. It has the same structure. So an electrochemical cell, a galvanic cell is an electrochemical cell that generates electricity energy from spontaneous redox reaction. So in other words, I can put this as from chemical energy, chemical energy to electrical energy. So in the galvanic cell, we will produce electrical energy, we will produce electricity from the chemical reaction. So that's the first one. The second one, we have electrolytic cell. So for electrolytic cell, it's an electrochemical cell that uses electrical energy to initiate a non-spontaneous redox reaction to occur. Okay, so in other words, for this one, okay, the energy change is from our electrical energy, okay, electrical energy to chemical energy. Okay, what does it mean here? Meaning for our electrolytic cell, we will use a component that has electric, so we will use battery over here to produce a chemical reaction inside our setup over here. For this one, we are using the chemical reaction to produce the electrical energy. And this electrical energy, like I mentioned before, is observed by the flow of electrons. So if you can see over here, we have electron moving in the circuit, okay, of each electrochemical cell. So this flow of electron, the movement of electron, that can cause electricity to appear or to occur. So before we look further on each electrochemical cell, we're going to look first on the important component in electrochemical cell. Okay, so what are the components that we need to look on? The first one, we will have electrodes. Okay, so this will be our first one, the first component that we're going to look, electrodes. So what is electrodes? So electrodes is basically object that conducts electricity between cell and its surrounding. So we have two types of electrode, not two types, we have two electrodes. In one electrochemical cell, we must have two electrodes, which is anode and cathode, which are dipped into an electrolyte. Okay, why must we have two different electrodes? Because one electrode will be used for oxidation process, the other one will be used for reduction process. Okay, so there are two types of electrodes. The first one, the first type, we have an active electrode. So this active electrode means the electrodes itself will involve in the half reaction, meaning the electrodes will either undergo oxidation or reduction. Okay, it involves directly in the chemical reaction, so it will appear on our chemical equation. So that's the first one. The second one, we have inactive electrodes. So inactive electrodes does not involve in half reaction. So for example here, graphite or platinum. So graphite over here is basically our carbon electrode. So what does it mean by inactive electrode? So this inactive electrode will not undergo any reaction. Okay, but why do we need that electrode itself? Okay, must it be present even though it's inactive? Yes, because an electrode is used as the place where chemical reaction will occur, and then it is used to complete our circuit, okay, our electrochemical circuit. So that's why it is very important for each electrochemical cell to have this electrode. So once you construct a chemical cell, an electrochemical cell, so take a look on what is the type of electrodes. Is it active or inactive? For you to get a clue on what will be the reaction that occur. Okay, so that's the first one, electrodes. The second one is electrolyte. Okay, so what is electrolyte? So basically, electrolyte contains mobile ions for conducting electricity. It can be in molten state or aqueous state. Okay, so for example, I give you like this. Okay, so I have a beaker. So inside this beaker, okay, I have Cu2 plus aqueous solution. So let's say Cu2 plus aqueous solution, it comes from copper sulfate. Okay, copper sulfate aqueous. So this copper sulfate aqueous, it will dissociate to become its ions. So Cu2 plus aqueous plus SO4 2 minus aqueous. And then this beaker, I want to construct an electrochemical cell. Okay, so I dip one electrode over here. Okay, and the electrode that I use is copper solid. Okay, so this copper solid is my electrode, and Cu2 plus aqueous over here is my electrolyte. So this electrolyte, it can either be in aqueous state or it can be in molten state. What does it mean if I say it's a molten state? So molten state meaning it's Cu2 plus liquid. Molten mean leburan. Okay, meaning from solid state, okay, you heat the copper metal until it melts. Okay, when it melts, it becomes in liquid phase. Okay, so if molten, like I mentioned before, it's from Cu solid to Cu2 plus liquid. Okay, molten or in liquid state meaning there is no water present. But if in aqueous solution over here, you have water present. Okay, so that's the difference between aqueous solution and molten state. So this one, the molten state and aqueous solution, we will discuss later a bit more when we talk about the second electrochemical cell, which is the electrolytic cell. Okay, but for this video, we're only going to focus on the aqueous electrolyte. Okay, so now let's discuss on the first type of electrochemical cell, which is the galvanic cell. So our galvanic cell, what are the components of our galvanic cells? So first one, we have anode and cathode, the electrodes, okay, where the chemical reaction will occur. The second one is voltmeter. So what is the use of voltmeter? What is the function of voltmeter in galvanic cell? So voltmeter is basically is an instrument that measures the difference in electrical potential between 2 points in an electric circuit. So in other words, this voltmeter is used to show us about the electron flow. How many electron flow and how many electric energy that we produce from a chemical reaction. Okay, so that's the function of voltmeter in galvanic cell. The third one is an external circuit. So basically this is your wire. Okay, and then the fourth one, we have salt bridge. Okay, maybe this is one component that is new for you, salt bridge. And the last one, our electrolyte, the solution that we dip our electrodes. Okay, so this is the setup for your galvanic cell, or we also call it as our voltaic cell. Okay, so where you have over here, so this is our electrodes, two electrodes over here. One is for anode and another one is for cathode. Okay, and then we have two separate beakers. Okay, and the beakers will contain an electrolyte compatible to the electrodes over here. If we are using an active electrodes. Okay, and then this is the external circuit, which is our wire, where the electron will flow inside the wire, and this is the voltmeter to record how many electron flows, to record how many electrics that is produced. And this is a salt bridge. Okay, this salt bridge is used to connect the two beakers over here and to complete our circuit. Okay, so as you can see over here, we're going to use this example throughout this explanation, where we have a galvanic cell that contains two electrodes. The first electrode over here, okay, the first electrode is zinc electrode, and then the solution that is used is zinc sulfate solution. So this is what I meant by the electrolyte must be compatible with the electrode. So if our electrode is zinc, so you will label this as zinc solid. The solution inside here, it must be zinc 2 plus aqueous. Okay, zinc 2 plus aqueous. Okay, it is enough if you just label as zinc 2 plus. Okay, and then the second electrode over here is copper. Okay, copper solid. So the compatible ion electrolyte for copper solid is copper 2 plus aqueous, and this can be found from copper sulfate solution. Okay, so if you can look over here, usually we will draw on the left hand side is our anode, and on the right hand side is our cathode. Okay, why must it be like this? So please recall back, if we have anode, okay, meaning the type of reaction that will occur, the redox reaction, the half equation that will occur at anode is oxidation. And then if we have cathode, the type of reaction that will occur, the half reaction that will occur is reduction. And this is fixed, regardless it is negative or positive terminal. Cathode will undergo reduction, and then anode will undergo oxidation. The species at anode will undergo oxidation. The species at cathode will undergo reduction. Okay, and then if you can see over here, we have electron flow. Electron is flowing, is moving from anode to cathode. Okay, so let me just write it down over here. Electron flow, it will always be from anode to cathode. Okay, why is that so? Because oxidation process here will produce electron. So electron is produced at anode. So that's why it will flow from anode towards cathode, where at cathode the reduction process occur. Reduction process over here, what happened? It will accept electron. Okay, so this is some overview of your galvanic cell. Now let's take a look on the detailed process on what happened at each electrode. Okay, at anode and also at cathode. So we're going to start with anode first. Okay, so now our anode, the electrode used over here is zinc electrode. Okay, so you need to make sure our electrode, it must be solid. Okay, compulsory, it must be solid. You cannot use something that is in aqueous phase or gas phase as electrode. Electrode must be solid. Wajib, compulsory. Okay. Okay. So, we're going to focus on this part first. Okay, this part over here, the one that I highlighted. Okay. So, zinc metal is immersed in zinc 2+ electrolyte, the solution of zinc 2+, like I mentioned before. So, zinc is more electropositive than copper. So, this one later we're going to look what is SRP table. So, SRP table here is standard, okay, sorry, I just put the name down, standard reduction potential table. Okay, let me change to another color so you can see. Okay, standard reduction potential. Okay, SRP. Okay, so this SRP table is used to determine the metal, the electrode that we use, will it undergo oxidation or will it undergo reduction? Okay, so I will explain it later how to choose which metal will undergo oxidation, which one will undergo reduction. Okay, so just for now, zinc is more electropositive than copper. Okay, so this means that zinc has more tendency to release electron. Okay, zinc prefer to release electron over here. Okay, so what does it mean by zinc prefer to release electron? It will undergo oxidation process. So zinc, when it releases electrons, it will produce zinc 2+ aqueous. So that's why zinc is the negative electrode. Okay, so for galvanic cell, our anode over here, our anode, okay, sorry, let me change to my highlighter. Okay, our anode over here is a negative terminal. So let me write it down as big as you can see. So this is negative. Okay, why is negative terminal? Because electron is produced here. Okay, we have electron produced over here, so that's why it is negative. Okay, so let's continue. So negative electrode produce electron at anode. Okay, so oxidation occurs at zinc electron, the zinc itself over here. Okay, the zinc solid over here undergoes oxidation. Okay, if it undergoes oxidation, what happens to the electrode, to the metal itself? Zinc metal will dissolve and the mass of zinc electrode will decrease. Okay, what does it mean by here? Okay, so let's say this is our zinc solid. Okay, when the zinc solid undergo oxidation, okay, what does it mean by the metal dissolve and the electrode, the mass of the electrode will decrease? So the zinc itself is being used, the zinc metal over here is being used to produce zinc 2+. Okay, so that's why the mass will decrease. Okay, what happened to the zinc? Okay, the zinc will produce zinc 2+ ion, and these zinc 2+ ions will enter the zinc 2+ solution. So that's why it is very important for you to have a solution over here, the electrolyte compatible to the zinc, to the electrode. So if you use zinc electrode, you must have zinc 2+ electrolyte. Okay, what happens if you use different electrolytes? Okay, if you use different electrolytes, a different reaction will occur and we cannot complete our galvanic cell. Now let's take a look on the other half cell. Okay, the other electrode, which is our cathode, the copper electrodes. Okay, so right now we are going to focus over here. So I highlight it over here. Okay, what happened on the cathode? So this is our cathode. Okay, let me highlight it with different color. So let me erase this first. Okay, cathode, positive. Okay, now, so at the cathode, over here, the half cell over here, we have here our copper metal immersed in copper 2+ electrolyte. So this copper 2+ electrolyte came from our copper sulfate solution. So the electrons from zinc, so as we discussed just now, at the zinc electrode over here at anode, what happened is zinc solid dissociate to zinc 2+ aqueous plus 2 electrons. Okay, the electron produced from our anode will flow through our circuit over here. Okay, and the electrons from the zinc metal will flow through the wire and enter our copper metal over here, our copper electrodes. So what happened inside this half cell? We have copper 2+. So copper 2+ will accept that electron. Okay, copper 2+ plus 2 electron, and it will produce copper solid. Okay, so copper is the positive electrode. So just now we mentioned negative here at our anode, it's negative terminal. Why is it negative? Because electron is being produced over here. So if this is our negative terminal, automatically over here is our positive terminal. So let me put it as positive. Okay, so positive terminal over here. Okay, so what happened? Copper is positive electrode and it will accept electron. So our cathode. Okay, so what's the observation can we see from our electrode over here, from the copper electrode? So reduction process, since it accepts electron over here, a reduction process occur. Okay, the copper solid deposited at the copper electrode. So what does it mean here? Okay, what does it mean? Copper solid deposited on copper electrode. Okay, so you have your copper electrode. Okay, initially this is your copper solid. Okay, when copper 2+ accepts 2 electron, what happened? Copper solid is formed. So where will this copper solid go? It will go on the copper electrode. So let me put as red color. So you will have extra solid around the copper electrode. So this is what it meant by the copper solid deposited. Okay, it stuck here on the copper electrode. So the mass of copper electrode will increase. Okay, what happened to the electrode is vice versa on what happened to the zinc. On the zinc, the mass decreases. Okay, dia berkurang. Mass decreases, berkurang over here because the zinc metal is used to form electrons. But on the copper electron, copper is produced. So copper will deposited, or in Malay, the terms that you will use is terenam. I think you use this on SPM. Okay, terenam or deposited on the electrodes over here. Okay, so that's what happened at our cathode, at the copper electrode. Okay, so this is what I've been mentioning a few times over now. Okay, electron flows from anode to cathode. Okay, let me highlight your anode. So here is our anode and here is our cathode. The electron will flow from our anode to our cathode. Okay, so the flow. Okay, make a bigger arrow for you. It will flow from here to here. Why? Again, because zinc produce electrons. Electrons will flow from here to copper. So copper 2 plus will accept the electron. Okay. Because there is a difference in electrical potential energy between the electrodes. So what does it mean? It has different electrical potential between energy, different electrical potential energy between the electrodes. So remember when I said about the SRP table, the value. So the value that we get from the SRP table is the electrical potential, and each beaker over here, each half cell over here will have different electrical potential energy. So that's why the electron can flow. And that difference in electrical energy will be shown on this voltmeter. Okay, so it will give us how many volts, okay, of electrons that have flow. Okay, we have finished discussing about our anode. We have finished discussing about our cathode. I even talked about the electrolyte and the voltmeter, also the electron flow. So the last part that we're going to discuss on our galvanic cell is the salt bridge. Okay, the component, the new component that you heard from this video. So what is salt bridge? So salt bridge contains a solution of non-reacting ions such as KCl, KNO3, Ne2, SO4. So what does it mean over here? Inside the salt bridge, okay, inside the salt bridge there is solution, and the solution, we use the solution that does not involve in the chemical reaction on these two half cells. Okay, so since here we have zinc 2 plus, here we have copper sulfate, so we just use any other salt solution. That's why it is called a salt bridge. Why is it bridge? It looks like a bridge. Okay, so for example, KCl. Okay, the most important part of our salt bridge, we must have a solution, a salt solution that can dissociate completely to its ions. So we will have here K plus and Cl minus. Same goes if I have KNO3. So it will dissociate completely into its ions, so K plus and O3 minus. So same goes with Na2SO4. So you will have Na plus and SO4 2 minus. We must have these electrons, these ions, the negative and positive ion. Okay, what is the function of salt bridge? Okay, we have two different functions of our salt bridge. The first one is to complete the circuit. Okay, without the salt bridge, the circuit, our galvanic cell over here is not completed. Okay, so the electron, when a circuit is not complete, then the electrical energy, okay, we cannot measure the electrical energy. And then second one, the most important function of salt bridge is to maintain the electrical neutrality of the cell. Okay, so let me discuss further about these two. So for the first function of salt bridge, to complete the circuit, I think you can see that very clearly how the salt bridge complete the circuit. Okay, the second function of salt bridge, how does a salt bridge maintain electrical neutrality in the whole electrochemical cell, in the whole galvanic cell? Okay, let's take a look one by one. So on the left cell, on our anode, so this will be the reactions that occur. Zinc solid to produce zinc 2 plus 2 electrons. Okay, what happened? So let me draw a quick sketch of your galvanic cell. So you need to make sure that you know how to draw your galvanic cell. So first you will have your voltmeter over here, okay, and then your wire, you will have 2 electrodes, okay, and then your 2 beaker, okay, and it is connected by a salt bridge, and then you will have your electrolyte inside here. Okay, so this is zinc solid, this is zinc 2 plus aqueous, Cu2 plus aqueous. It needs to be labeled with the phase, and then this is copper solid. Okay, we have our galvanic cell over here. So on this part, on the left cell, okay, before that, okay, inside our galvanic cell, inside our salt bridge over here, we have KCl, so K plus and Cl minus. Okay, so that's what I have in here, Cl minus. Okay, back to the explanation. Okay, zinc solid produce zinc 2 plus 2 electron. Okay, so what happened is zinc 2 plus over here from our zinc solid will enter the zinc solution, zinc 2 plus. Okay, zinc 2 plus, the newly formed zinc 2 plus ion. Okay, when this zinc 2 plus ion enter the solution, what happened? The solution over here, it becomes more positive. The overall excess, we have an overall excess of positive charge. So initially, we already have zinc 2 plus, the blue color one over here. When the zinc undergo oxidation, it will produce zinc 2 plus ion. So the new zinc 2 plus ion will combine with the one that is already there inside the electrolyte. Okay, so you will have overall inside this beaker is very positive. Okay, very positively charged. So that's why it says over here, overall excess positive charge. So for our galvanic cell, we want it to be neutral, to be stable. When it is too positive or the half cell is too negative, it is not balanced. Okay, how are we going to balance this? Okay, we're going to balance this by the use of our salt bridge. Okay, over here. Okay, the component inside the salt bridge. So since over here it is too positive, okay, the component from the salt bridge, which is Cl minus, will move towards the half cell, towards anode. Okay, like I said over here, the Cl minus ions from the salt bridge will move into zinc 2 plus half cell, and when the Cl minus, it has a negative charge, it will neutralize back the half cell over here. It will neutralize the zinc 2 plus added. Okay, just to neutralize the charge. Okay, Cl minus will not react with zinc 2 plus. So the function of Cl minus is solely only to make the overall charge become neutral. Okay, so I hope you understand that. So that what's happened in the first half cell in our anode. Okay, what happened to the right cell, our cathode? So inside cathode, copper 2 plus will accept electron to produce copper solid. Okay, so what happened over here is we have our copper 2 plus. So this copper 2 plus will undergo reduction. It will accept electron and become copper solid. So what happened? The concentration of copper 2 plus will decrease. So when the concentration of copper 2 plus decrease, it will become less positive. Okay, when it is less positive, meaning overall it will become more negative. So as stated over here, copper 2 plus ion leave the solution, causing an overall excess of negative charge. So where does this overall excess of negative charge came from? From the electron. So how will the salt bridge helps to maintain this the neutrality? Okay, so since it is more negative right now, what will happen is the K plus ion over here. Okay, the K plus ion will move towards the half cell from the salt bridge towards the cathode to make sure that the electrical charge over here is balanced. The plus charge and the negative charge is balanced. So K plus ions from the salt bridge move into the copper half cell to maintain its electrical neutrality. So that's why even though the reaction keeps on happening, keeps on occurring, but the electrical charge is still maintained. The half cell is not too positive and it is not too negative. It is neutral. What will happen if there is no salt bridge inside our galvanic cell? So this is what will happen. We focus here on zinc. As the zinc rod dissolves, the concentration of zinc 2 plus in the left beaker increases. Okay. So as it increases, the reaction will stop because the net increase in positive charge is not neutralized. It just becomes too positive over here. Okay. Over here, it becomes too positive. Okay. When it becomes too positive, the electron flow, we can say it will stop the electron flow. Okay, so that's why. So as a conclusion from the discussion about the salt bridge, you just need to know what's the function of salt bridge. 1, to complete the circuit. 2, to maintain electrical neutrality. Okay, so that's all. Right now, we're going to look on the redox reaction in the galvanic cell. So what will happen in the galvanic cell? Okay, the half equation. So this is as we discussed over and over again. So at anode, we will have zinc solid to produce zinc 2 plus and 2 electrons. And then at the cathode, copper 2 plus aqueous plus 2 electron to produce copper solid. So the redox reaction, the overall equation redox, will be written down like this. Okay, this is like the one that you have learned before. So we're going to combine these two equations, the oxidation and reduction, by making sure that the number of electrons is the same. Okay, once the number of electrons is the same, you can cancel the electron. So cancel, and then you will have your overall equation over here. Okay, so right now we're going to look on cell notation. So this is new for you. The redox equation is something you have learned from last semester. Okay, right now we want to write down a cell notation. How are we going to write down this cell notation? Okay, so this is our cell notation. So let me just scribble something over here. So zinc to zinc 2 plus, copper to copper 2 plus. So zinc to zinc 2 plus is the one, the oxidation reaction that occurs at anode. Okay, oxidation. And then copper 2 plus to copper solid is a reaction that occurs at cathode. Okay, which is our reduction process. Now, how are we going to write down the cell notation from this redox equation? So this is our redox overall. Okay, so this is your cell notation. Okay, so let's take a look on what we have in our cell notation. Okay, the first one, anode is on the left hand side. So overall over here, this is the one to show your anode. It will show the oxidation process. And then on the right hand side over here, this is your cathode. Okay, it will show your reduction process. Okay, next, as you can see over here, there are some few things inside the cell notation. The first one is this one. Okay, palang ni. Okay, so what does this represent? Okay, what does this one line represent? So it represents the phase boundary. So it is used to separate different phases. So for example, here zinc solid, here is zinc 2+. Okay, whenever we have a different phase boundary over here, we will put this line over here, one line over here. Okay, and then the next one, we have a double line over here in the middle. Okay, double line over here. So what does this double line means? It represents the salt bridge. So this double line is just to show that the left hand side over here is our anode, is one half cell. Okay, and then on the right hand side is another half cell. Okay, and these two half cell is connected by a salt bridge. Okay, so if you can see over here, from the cell notation, okay, on the left, on the end, at the end of the cell notation, as you can see, it is solid. This represents our electrode. Okay. Okay. At the end, we must have our electrode over here. And then in the middle here, we have our electrolyte. So at the end, compulsory, wajib, mesti solid. Okay, electrode on the left and on the right hand side over here. In the middle is your electrolyte. And then the phase over here, compulsory. You must write it down. Okay, and then zinc 2+, since it is an aqueous solution, you need to mention the concentration. This is also compulsory. Okay, because later we're going to look on a reaction that occurs at standard condition and non-standard condition. Okay, so if we have 1 molar over here, meaning it is at standard condition. Okay, so comma is used for components that are in the same phase. Okay, what do I mean by this? So this is an example. Okay, so graphite I minus aqueous, I2 minus solid, H2 aqueous plus MnO4 minus aqueous, M2 plus aqueous, graphite. Okay, so basically this is an example of a cell notation. So like I mentioned before, on the end of each side, left hand side and right hand side, okay, graphite is our electrode over here. So this is electrode, this is electrode. Okay, it will be solid. It needs to have solid actually over here. So as you can see over here, since the graphite is the electrode, meaning we have an inactive electrode. Okay, so the reaction will occur inside here. So I2 aqueous, and then you have I2 solid over here. Okay, and then we have the salt bridge, H plus aqueous, comma, MnO4 minus aqueous, comma, Mn2 plus aqueous. Everything that you see over here is actually a chemical reaction that occurs at cathode. Okay, we put the comma sign over here just to show that it is a different substance, but it has the same phase yang sama. Okay, we put as comma. But if it has different phase, we will put this line, okay, to separate aqueous and solid. So another thing that I want you to see, okay, from the cell notation, actually you can see a chemical reaction occur. So at anode, you know the chemical reaction that occurs is oxidation. So it's from zinc solid over here to zinc 2+, oxidation. Okay, and then over here from copper 2+ aqueous to copper solid. So this is reduction. Okay, the same process occur over here. So different chemical cell will give us different cell notation. Now, how do we know which metal is anode or cathode? Okay, like I mentioned earlier before, how do I determine zinc will be the anode and copper will be the cathode? Okay, I mentioned about SRP, the standard reduction potential table. Okay, so this is your standard reduction potential. Okay, what is actually I meant by when I said look at the value on the SRP table. So this is the value that you will look. So in the SRP table, you will have each half reaction is written as reduction. So by the name itself over here, standard reduction potential, meaning how easy the metal to undergo reduction. So the value over here, negative 0.76 and positive 0.4 is the value on how easy the reactants over here, okay, it's not the metal, sorry, the reactants over here to undergo reduction. Okay, so the more positive the E0 value, so the E0 over here, okay, this is what we call as E0 half cell. Okay, the more positive the E0 value, the higher the tendency to undergo reduction. So we will choose as our cathode. The more negative, okay, more negative the E0 value, the higher tendency to undergo oxidation. Okay, we will put at our anode. Okay, to make it simple, okay, the target over here is this is the value from your SRP table. Okay, this value over here, what does it shows? It shows the ability to undergo, to undergo reduction. The more positive the value or the bigger the value, okay, the more positive the value, the easier it is to undergo reduction. So between zinc 2+ and copper, the one that will undergo reduction is this one, the positive one. Okay, so that's why we choose copper 2+ over here to become our cathode. So automatically, this one, zinc, will become our anode. So that's why we choose zinc solid as the electrode at anode, because it needs to undergo oxidation. Okay, and then we will choose copper electrode on our cathode because it needs to undergo reduction process on cathode. Okay, so just now I mentioned about standard electrode potential E0 half cell. So what is it? Okay, so the standard electrode potential is a measure of the ability of half cells to attract electron toward itself at standard state. So, in other words, like I mentioned before, ability to undergo reduction process. Okay, this is shown at the value of our E0 half cell. half cell. Okay, why do I mention E0 half cell? Because later we have E cell, E0 cell. Okay, E0 cell is the combination of the two half cells. But to determine which will become cathode, which will become anode, we will look at the value of the E0 of the half cell. Okay, so if you look over here on the E0 half cell, E0, okay, half cell. The half cell over here, for example, the one that I did just now, zinc 2 plus with zinc. So this is the half cell that I'm looking at. Okay, and then you have a knot value over here. So this knot value refers to standard state. So our standard state, 1 atm pressure for gas, 1 molar for solution, and pure solid for electrodes. Okay, so the magnitude of the electrode potential depends on the tendency of the metal or non-metal to lose electron. So this is what I mentioned just now. To choose, meaning over here is to choose cathode. Okay, to choose which one that will be our cathode. Okay, the more positive E0 cell, okay, E0 half cell, or the bigger E0 half cell will be the cathode. Okay, because it has more ability to undergo reduction process. It can go undergo reduction easily. Okay, so our E0 cell, it can be E0 anode or E0 cathode. So the E0 anode and E0 cathode just refer to where the position is. Either it is at anode or cathode. So just now, if our anode is zinc and then our cathode is copper. Okay, so what we will have over here is E0 anode will be written down as E0 zinc 2 plus zinc. Okay, and then E0 cathode will be written down as E0 Cu2 plus Cu. Okay, so the way you write this down is the same. Okay, the same as the one that you take the value from the SRP table. We will discuss this more later on the next video when we start doing the calculation, the simple calculation for finding the E0 cell. Okay, but for now, we just need to understand what is this standard electrode potential. So this is what we call as the standard electrode potential, the half cell, the ability for that particular half cell to undergo reduction. The easier to undergo reduction, the more positive the value of the E0 half cell. So the more positive the value, we will choose that particular electrode, that particular half cell to become cathode. The less positive one will become anode. Okay, this will be the end for this video. So on the next video, we will discuss more on the galvanic cell and how to calculate the E cell. Okay, so for now, thank you for listening so attentively, and until we meet again on the next video. Thank you guys.